Okay, if he arrives, maybe we should stop and go back and say hello. So let me just start by summarizing what I did not explain, or what I explained briefly yesterday about this critical exponent, which will appear at the end of this lecture. And today I want to discuss another application of the techniques to the study of group actions. So we have already seen group actings on the hyperbolic manifold with compact quotient. Yesterday a group was acting maybe without compact quotient, and today will be quite general. So if I start by the picture that I drew yesterday. So this was supposed to be the quotient of the hyperbolic space of dimension n by some discrete group of isometries. And I explained the construction of a map using this barycenter, which was working on this space and pushing things in one or the other direction. And the consequence was an estimate of the critical exponent, which was defined yesterday, of this group here. So if I can summarize the theorem that I stated yesterday, but did not prove completely, but that's not really the problem. In fact, we can forget about this amalgamation and just keep in mind this group. So the theorem could be stated as follows. If we assume that the injectivity radius of, so maybe I call it x, of x is positive, and if we also assume that, say, some homology group is not zero, say, for example, hk of x with real coefficient is not zero, then the proof that I sketched yesterday shows that then the critical exponent of this group, C, is greater or equal to k minus 1. Of course, there are some equality cases which are sharp, and I describe a little bit the equality case. It occurs when, so when the equality is achieved, there is a cycle which is totally geodesic. So yesterday I was only interested in the n-1 dimensional homology, but the method would apply to a quite general situation. So there is some, so this is some hypothesis which prevents the presence of cusps. If you are used to that, cusps would have a form like this with cycle arbitrarily small. But if we forget about this, this is a topological assumption, and the conclusion is one property of the group. It says that the group has to be big. If you want to have some cycle in some homology which is not zero, you need to have a quite big group, and big is the critical exponent which was defined yesterday. And I don't recall the definition, it's pretty easy, but let me just recall that this is the critical exponent of C. And of course, this could be extended to the case when Hn is replaced by a negatively curved manifold. But that's not, my purpose is not to give the most general situation, just to describe the technique. Okay, so this will probably appear at the end of this lecture, if I can reach the end. Well, I reach an end certainly, but which end we'll see. All right. So today I want to talk about uniform growth of groups. So you know that geometry is closely related to group and group action. And I will start with the abstract study of group and then see them acting on manifold. So let me start by gamma. Well, all my groups are supposed to be infinite and enumerable. So let me assume that I have a group of finite type that is a group with a finite set of generators, and I'll pick up a generating set, and for the sake of simplicity, I will assume that it is symmetric. So let me call sigma I up to sigma n the generators, and I'll put in the generating set the inverse, which is something we do quite often. So a group of finite types, that is, it is finitely generated, and I pick a symmetric generating set. Finite, of course. We could take the full group as generating set, but it would not be so clever to. But so I precise that I want infinite group and finite generating set. So let me give two definitions. The first one is the definition of a number which characterizes the size, the asymptotic size of the group, which I will call the entropy of the group gamma, related to this generating set. And the definition is a definition like for any kind of entropy. So it is the limit or lim sup when r goes to infinity of 1 over r logarithm of the number of element yeah, maybe I should say it, start to say it differently. No, let me do it this way. There are several ways to define it. The number of elements such that the length with respect to the generating set of these elements is less than r. So I will define this number in a minute, well, in a second actually, but this is to be thought as a length, hence this is the cardinality of some ball of radius r, and well, since we are in a discrete space, cardinality is like a volume in general. So what is this length? So this is the first definition. Second definition, which should be maybe first, length of gamma. Well, if you take an element gamma, you can write it in terms of a generating set as a product, P I1, sigma I2, P I2, and so on, a finite product of powers of elements of the generating set. Then the length would attribute length 1 to all elements of the generating set. So the length of this element should be the sum of the absolute value of the pi, so my notation are bit pil. Okay, so you count the sum of the absolute value of these numbers, absolute value because it could be negative. And of course, there may be different way to write a given word as a product of element of a group, because the group may have some relations. And so I'll just take the infimum over all possibilities. All right. So this corresponds, actually, Hervé mentioned that yesterday. You see that I cite you in every lecture, and you don't do the same for me. So Hervé mentioned it yesterday, corresponds really to computing the length in a metric space. So the metric space, is it okay if I write on this blackboard at the end? Yeah, okay. So the metric space is the so-called Cayley graph. So you should be careful. So let me call it C. And one should be careful that it does depend on the generating set. And the way to construct it is quite well known. You start with a vertex at the neutral element, and then you add edges for each element of the generating set. So let me do only two, sigma 1. So sigma 1 corresponds to this vertex, sigma 2 here, and of course the inverse are also here. And you keep going. And you get a graph. So far it is a tree, but there may be some relation corresponding to cycles and so forth, so on. Okay. So this is the Cayley graph. And Hervé explained yesterday that, so you make it into a metric space. Let me call d sub s the distance, which is nothing but saying that each edge has length 1. Okay? And so Hervé explained yesterday that we can talk about hyperbolic groups in the sense of Gromov if this graph with this distance is hyperbolic in the sense that it is defined yesterday with thin triangles. So now you can check that if you take an element, writing this element as a product of element of the generating set consists in choosing a path going from the neutral element to this. So say gamma is here. And as you can see, there are several paths. And you choose the shortest one, which is supposed to be the geodesic. Okay, and so this set here is nothing than the ball with respect to this generating set, or maybe I should call it ball in the Cayley graph, well, centered at the identity element and of radius r. So since it is discrete, cardinality the same than volume. So this is exactly the definition that we are used to, that at least that I gave yesterday, for the entropy, in the sense of volume entropy. Okay, and the third thing I want to define here is the so-called algebraic entropy of the group. And this is nothing but the infimum over all entropies here when you let S vary among the finite generating set. So this is the infimum of, so what are my notations? Entropy sub S of gamma for S generating set which is finite. Well, it's not completely necessary to take symmetric sets, but I mean, it helps sometimes. All right, so that's why it would be stupid to take infinite generating set, because we would take the full group, and then this number would be 0, so meaningless. Okay, so the question I want to address today is the following. So I'm sorry, I should start by two others definition. So, one, the group gamma is said to be to have exponential growth if the entropy of gamma with respect to one generating set is positive. So yesterday again, Hervé made the remark that if you change a generating set, you get two spaces which are quasi-isometry. Here you can check that if you change a generating set, this property is preserved. So it's said to have positive exponential growth if for one, hence for all, generating set, finite of course, this quantity is positive. And in the title of the lecture, I mentioned uniform growth. So now gamma is said to have uniform growth if the infimum is positive, which is much stronger. And what I want to discuss is the gap between these two definitions. In fact, it was a question and I guess asked by Gromov in the 80s, well, 1980s. Which is it true that uniform growth, no, I'm sorry, is it true that exponential growth implies uniform exponential growth? Well, here I should add uniform exponential growth, of course. At the time when the question was asked, we had no example, no counterexample, of course, otherwise you would not have asked the question. But all the examples were groups for which the answer was yes. So as such, the answer is no. So let me make a quick history of what is known, and not exhaustive, certainly. Certainly the answer is no. But one had to wait 2004 and a very complicated example due to Wilson, who gave the example of a group which is exponential growth and not uniform exponential growth. Okay, so the answer is no, but I mean, for most cases that come from geometry, the answer is yes. So let me give a short list of groups for which the answer is positive. So how does it start? So there are the examples of solvable group. So it's a result due to some Russian ozin. Then the example that we saw yesterday, amalgamated group. So I gave the definition yesterday, just this free product where you mod out by a subgroup which injects in both parts. Well, this is easy to do, but I think it's due to Bücher and maybe there is umlaut and de la Harpe. There is no, he's from French Switzerland. So de la Harpe has written a book on geometric group theory, and you'll find in this book plenty of very nice information. So it's a very good book, actually. More interesting, well, this is interesting, but more interesting for geometers is the category of hyperbolic groups. So it's a result which is due to Max Kubi. And so what is an hyperbolic group? As Hervé said yesterday, it's a group for which the Cayley graph is Gromov hyperbolic. So by hyperbolic, I mean here Gromov hyperbolic. So it's a quite general situation. Well, if you don't see what it means, and I would understand because I don't see either, you should keep in mind the following examples. So if you take a compact negatively curved manifold, then its fundamental group is hyperbolic. So this class is seems to be very large because it contains all fundamental groups of compact negatively curved manifolds. I said seem to be a large class, but if you try to exhibit examples of negatively curved compact manifold, you'll see that there are not so many examples, explicit examples, I mean. Of course, if you have a symmetric space, like a compact quotient of the hyperbolic space, then you can move the metric and keep it negatively curved. But it's cheating because the fundamental group has not changed. So apart from the symmetric space of negative curvature, there are examples, but very rare. And I guess that's why Gromov introduced this notion of hyperbolic groups, of weak version of hyperbolicity that Hervé described yesterday, to widen the class of objects you can work with. Okay, so this is a small class, actually. Well, as far as explicit examples are concerned. Okay, and finally, this is the example which is a model for us. It's, you may take discrete subgroups of linear groups, so say J ln K, where K is a field. And there are two different results, actually. So if the, or maybe I should keep that. If the characteristic of K is 0, then this is due to Eskin, Moses, and Roux. And if the characteristic of K is positive, like for example, if K is a field of periodic numbers or polynomial with coefficient in periodic numbers, then this is due to Breuer, Emmanuel Breuer. So for linear groups, this property is true. In fact, let me be more precise. One can state a more precise theorem. So let me state the EMO version. So if characteristic, maybe I should write it, of K is equal to 0, then there is an alternative. So for those who know, the Tits alternative is very similar. And gamma, the group gamma is either almost nilpotent. So these are words that I wanted to pronounce, and I will describe what it means. Or it has uniform exponential growth. So it's more than that because, well, let me define nilpotent groups, and I'll make the comment after, well, almost nilpotent. So is everybody familiar with nilpotent groups? Which is not a difficult notion. So let me just recall that almost nilpotent means that there exists a subgroup of gamma, a finite index, so I'll denote the index as we usually do with this bracket. A finite index is in gamma such that gamma prime is nilpotent. When all properties which come from geometry, you have to have this almost thing involved. So the geometric understanding of this almost mean that say gamma is a fundamental group of a manifold, then there is a finite cover which corresponds to a subgroup of finite index, a finite cover such that the fundamental group of the finite cover is nilpotent. Okay, so it's more than that because you may know, or you may check, that's easy to do, that a nilpotent group has polynomial growth. So this statement says either the growth is polynomial or uniformly exponential. It's more because between polynomial and exponential, there are some groups with intermediate growth. So if you work with a linear group, then you get a stronger answer.
So you see the counterexample, well, it's not a conjecture, but the negative answer to this question, the negative answers are very rare at the moment. All right. So what I want to describe today is a non-linear version of this result by Esking, Moses, O, and Breuer. So let me make a statement. So I start with the simply connected, the so-called Hadamard manifold. So simply connected and negatively curved manifold, and I will assume that the curvature is, the sectional curvature is pinched between two negative numbers. For today, I mean, could be relaxed, but that's sufficient. And the theorem I want to address, which is a theorem of Courtois, Gallo, and myself, is if a group gamma acts discretely and faithfully, this is stupid. I mean, I should have said a discrete subgroup of the isometry groups by isometries on X, then gamma is either almost nilpotent or as uniform exponential growth. Exactly the same statement, with the extra outcome that we can give a lower bound of the algebraic entropy, which is explicit. That will please Kerr probably, and which depends on the dimension and only on the lower bound of the curvature. Strictly positive. So we can compute a number which depends only on the dimension, and this A over there, such that we bound from below all algebraic entropy of groups acting as discrete subgroup of isometries on Hadamard manifold with these curvature conditions, sectional curvature conditions. And again, the method is the one that I've described in the first lecture, second lecture. Well, it's a variation, which is a more drastic variation actually here. Okay. So before sketching the main ideas, let me describe what did I plan to do, some the classification of isometries. So I will give I will recall the classification of isometries of the hyperbolic group, of the hyperbolic space, I'm sorry. And the classification is the same for simply connected manifold of negative curvature. So I figure that you are familiar with the classification of isometries of the hyperbolic space, but let me recall this because I will use them explicitly, actually, later. Okay, so let's go to describe the isometries, the three classes of isometries. And say, to make it simpler for the hyperbolic space, and I want to take the two-dimensional hyperbolic space. It's even simpler. Okay, so let me draw the two-dimensional hyperbolic space. So this is the half space in R2. And let me recall that the metric is dx dy over
y square. So maybe there is a 4. Probably there is a 4. I'm not sure, but it doesn't really matter. Where y is this direction, is positive, and x, of course, is the x-axis. So the three kinds of isometries are hyperbolic, parabolic, and elliptic, like the three kinds of geometries. Okay, so let's start with the hyperbolic. So the key example is given by gamma. So if you allow me, I'll use z for xy, for the point xy. And so gamma z equal lambda z with lambda a positive number. So from the Euclidean side, it's an homothétie, but it is an hyperbolic isometry. It amounts to the action of the matrix. So let me try to be square root of lambda minus 1. So if you let this matrix act as, so this matrix is in SL2 of R, which is the isometric group of the hyperbolic space, and a metric A, B, C, D acts by Z, AZ plus B over CZ plus D, as usual. So if I'm not mistaken, this is obtained by the matrix that I give. And okay, so what are the features of this isometry? Well, there is this line which is preserved, and on which, for the hyperbolic metric, the action is by translation. It looks like an homothétie, but if you compute the distance, it's by translation. And all these lines are preserved, but they are not geodesics. So if I switch to the other model, which I draw here, and I will use this, and that's why I take some time to describe, to recall this. So if I switch to the ball model, and this is my favorite picture, as usual, then the vertical line is a geodesic, which is called the axis of the element gamma, hyperbolic. Gamma, okay. On this axis, the action is by translation. And away from this axis, it preserves these lines with a slope which correspond to the curve which are at constant distance from the axis. Now, if you look at the action at infinity, this point is fixed, this point is fixed, and away from these 2 points, the whole mass is sent close to the attractive point. If you iterate, then everything, all the matter of the sphere will be sent, the circle will be sent to this point. I'll use that later. Okay, this is easy example. Now, gamma is said to be parabolic if it corresponds to this kind of matrix, say U here, and the action is simply the translation. Z gives Z plus U, where U is a real number. So it preserves horizontal line. And in this picture, it preserves horocircles, which correspond to horizontal lines. So the action moves on the horocircle in one direction and preserve all of them. And of course, the point at infinity, which is the common center of all these horocircles. All right. And the last family are the elliptic element. Well, it's not fun to give the formula for elliptic element here, but I mean, elliptic element means element which fixes points. For example, this one. So around this one could be rotation. So they have a fixed point inside. Maybe this is too low in H2. So here there is one fixed point at infinity. Here there are two fixed points at infinity. Here there is one fixed point inside. And this situation is general for negatively curved Hadamard negatively curved manifold. It's not true for non-positively curved. But there is a classification also. All right. So this is easy. Let me recall another property that I want to use. Probably it's better if I keep this picture because I'm drawing the same thing. So let me recall the so-called Margulis lemma. So this is a beautiful property that Margulis discovered. So in the situation that we had before, so gamma is discrete group in the isometric group of X. So certainly the curvature assumptions are too strong here. The upper bound is not necessary. But let me stay in this setup. And the dimension is n. Then there is a number, which I'll call mu, which depends on the dimension and the lower bound of the curvature, which is positive. So that if one looks at the following group, which I call gamma mu of X, which is the group generated by, so I don't know how to write generated by, let me write generated by the elements gamma in the group capital gamma, such that, I write down here, the displacement at X is less than mu. Then Margulis' lemma says that this group is almost nilpotent. And this is a very nice and strong property. Mainly of, what I'm saying is wrong, let me say anyway, mainly of negative curvature, but of course it's valid in a more general situation, which says that if you look at these elements which displace a little bit a point, just less than this quantity, and this generates subgroups of gamma, and this subgroup is small. In fact, small means almost nilpotent, virtually nilpotent, sometimes you say. So you can check that in the real hyperbolic case, then what you get here is more than nilpotent. You could put a billion, almost a billion. But it's not true in general, and there are examples like complex hyperbolic space for which you could get like something like an Heisenberg group, which is nilpotent and not abelian. So this actually introduced a quantity which is the displacement at a point. So let me give a definition. So start with a group and a finite generating set. And I look at the displacement of a point by element of the generating set and the maximum for all elements of the generating set. So the point is fixed. And let's look at the minimum, the infimum over all X. X is the name of the manifold, yes. And this I'll call L of S. And maybe to make it simpler, later I will use L only. So a corollary of Margulis' lemma is that this L of S is greater or equal than this number mu if gamma is not almost nilpotent. So we have a way to start the proof. So in the theorem that I stated, there was an alternative, either almost nilpotent or something else. So the way to start the proof is to assume it's not almost nilpotent and prove there's something else. And the start is, we have this, which means that there are places, lots of places where when you look at the displacement of the generating set, it displaces a lot. Well, a lot. More than this quantity. Okay, in fact, I want to cheat during this talk a lot. So I will assume, so let us assume that the infimum is achieved at some point. I mean, the difference between this assumption and doing without assumption are just technical issues which I don't want to discuss. But let me assume that L is equal to the max of this distance of x sigma x, well, in fact, at some point, achieve at some point, which I call x naught. So this point x naught has this property that if you look at the displacement by the elements of the generating set, there is certainly one which is at most L, or which is exactly L, actually. Well, this is an easy exercise to check that necessarily all displacements by element of the generating set are equal to L. Otherwise, you could move a little bit and lower this quantity. So I let you check that if this is achieved at x0, then for all sigma in S, the displacement is, say, equal to L. So there is a point which is kind of optimal for this number, where all elements of the generating set, say sigma 1, sigma 2, and of course the inverse by isometries, displace, sorry, I should write it this way, which is much better, displace of a distance exactly equal to L. Let me make, I think well, this is true. I think this is true. Let me make this assumption anyway, just to simplify the discussion. And that is the start of the proof. There is a point where the displacement of the generating set is quite big. Now you may ask, how can one show that the algebraic entropy, at least for a generating set, is large? Let me describe the most classical method. That this number, how to show that this number is, say, positive. So there is a very classical method which amounts to, we know groups for which this number can be computed and for which it is obviously positive. It's a free group in at least two generators. So if you can find alpha and beta, two elements in gamma, so I have to check my my notation, so that the distance to the origin is less than, say, a number which I called A. So these elements are not very far from the origin in the Cayley graph, and you assume that they generate a free group, or even less than a free group, a free semigroup. So what is a free semigroup? Well, a semigroup means that you take only products of positive powers of alpha and beta. So you look only at elements of this kind, P, I, K, beta, Q, I, K, elements of this type with P, I's and Q, I's positive. Then I can let me draw the picture for alpha and beta. So this is E, this is alpha, this is beta. Starting from here, you have two possibilities, alpha, beta, or alpha square. And here, two possibilities, beta, alpha, and beta square, and so on and so forth. So, I mean, it's a free group, or free semi-group, so there are no cycles. So the number of elements at the first generation is 2. The second generation is 4. At the nth generation, it's 2 to the n. And the growth is exponential. 2 to the n is exponential. So if you can produce this not too far from the generating set, then you'll get a lower bound for the algebraic entropy, well, the entropy with respect to this set. And this is obvious to check. One can easily check that the ball of radius n in the big group gamma, how can I? Yes, the ball of radius n in the big group gamma. So here I need more notation. So gamma and related to S contains the ball of radius n divided by A. A is an upper bound for the length of these two elements. In the group, the free group generated by alpha, beta, and with this generating set. Of course, if you go to distance in this free group which I have drawn here, if you go to distance, say, k, then since the length here is less than a, it means that in original group, you went to a distance less than k times a. So this is just what I'm saying here. And what we have just seen is that the cardinality of this ball here is something, well, it is like 2 to the n over a. Of course, it may not be an integer, but never mind. So now you take the logarithm here, you divide by n, and what you get is that the entropy of gamma with respect to S is greater or equal to log of 2 over a. All right? Really straightforward computation. Huh? Very baby calculus. But this says that if you want to force, I mean, to check that the entropy with respect to a given generating set is big, well, is not 0, you have to find, say, two elements which generates a free group or a free semi-group, whatever, it doesn't really matter, which are not too far from the origin. Otherwise, if A is big, then this becomes smaller and smaller. And this is the issue which is the most difficult. So there are groups for which this is not possible, but nevertheless, they have exponential growth and even uniform exponential growth. And this is the discussion that this is the problem, in fact, in the theorem that I want to describe. Okay, so this is the classical technique. Now, how can we produce such couple of elements in our situation? Okay, so now let me go to the proof, well, to a sketch of proof, or the ideas of a proof. Of the theorem. So the theorem in itself is not revolutionary, but it's a good opportunity to discuss different topic. I'm very slow, but it doesn't matter. So I will. So there is an alternative. And let me assume. So the first step is to assume that there is an element gamma in the group gamma, not too far from the identity. So in fact, in our work, it's 4. But you can forget about this 4. It could be 5 or 6. It's just not too long, such that the length of gamma, which I did not define, but I define now, which is the infimum of the displacement, which is sometimes called the displacement of gamma. over all x is not 0. So say bounded below by some number, which I call delta, and which has to be chosen later. So this is a so-called displacement of small gamma. So this is something that I did not describe. In the three categories of isometries, so if you compute this infimum, for the elliptic element, of course, it is 0 because there is a fixed point. For the parabolic element, it is 0 because when you go to the point at infinity, which is the fixed point here, then the distance between x and gamma x decreases. But for the hyperbolic element, it's not 0. And this is a characterization of hyperbolic element. So you can check that if you go to the point at infinity, which is fixed, then it's not 0. It's even bounded below. So this implies that the element gamma is hyperbolic. And in fact, it's because we made the assumption that the group gamma is not almost nilpotent, one can check that there is a second one. So you can produce the second one just by conjugating. So if you look at all conjugates by element of the generating set, you can produce a beta. So it's not difficult to show that you can produce a second element beta, which is a conjugate of this one, which has the same property. And in fact, the length of a conjugate, the displacement is the same than the displacement of gamma. The only difference is that the axis, these are two hyperbolic elements, are different. So beta has the same property. So now I come back to the picture. So we have one hyperbolic element with its axis as such, and a second one, beta, with the axis which is different. And whose displacement is quite big. It's bounded below by this delta that has to be chosen, but let's assume that it is big. Think of delta as being big. It's not true, but you can work out, one may work out the difficulties. Then what I want to show is that this gamma and beta generates a free group or a free semigroup, say a free group. So this is the classical technique that you probably all know, which is called the ping-pong lemma, which I think goes back to Tits. Probably Tits introduced that. So how does it work? Let me describe this. You're probably familiar with that. If it's too easy, you just stop me. If you don't stop me, I keep going. You don't stop me, so I keep going. So because these elements displace a lot, I made this assumption, you can draw 4 sets, or maybe only 2, but let me make it simpler with 4 sets, like this, around the fixed point. So these sets will be denoted A, B, C, D, and say gamma pushes in this direction and beta too. And I will assume so that you can produce these 4 sets, which are disjoints, 2 by 2, and with the following property. Gamma is so big that except from this point, it sends almost everywhere inside this set. So more precisely, gamma of the complement of B is included in A. And of course, the same with the inverse. Gamma inverse with the complement, send the complement of A in B. So this is a standard action of conformal transformation on the sphere. They push everything to a point if they are hyperbolic. But I assume that I can produce 4 sets like this, and the same with beta, C, and D. Okay, then now we can show that the group or the semigroup is free by the classical argument, which I recall. So let me assume that there is a word W, which can be written gamma P I Y M Q Y1 up to gamma P I K beta Q I K, and that this word is equal to the identity, which means that there is a relation and the group is not free. Okay? So for the sake of simplicity, I will assume that the PIs and the QJs are positive. It's not necessary, but I do it for simplicity. And you can always arrange yourself just by conjugating this element so that if it starts with beta, it ends with gamma. If there is a gamma here, you conjugate, multiply by gamma minus 1 and gamma. It won't change the relation, and you can put all gammas on one side, all betas on the other side, for the 2 sides, not in between. Now pick a point where? Here. Let's pick a point X here and look at the image of X. Okay, so beta to a positive power, because of the property which is not written, send everything which is not in this ball into this one. So X is already there. So beta of X is included in C. Now if you apply gamma PIQ, IK to beta QIK of X, gamma to a positive power sends everything which is not here inside A. So in particular, this beta of X will be sent here. So this is in A. I'm sorry, this is A, this is in A. And you keep going, and you see that when you reach this gamma, everything will arrive in A. On the other hand, because we assume that this is equal to the identity, this is X, which belongs to C. And this is a contradiction. So this is a contradiction. And it shows that the group generated by gamma and beta is free. So in our proof, we cannot show that there are free groups, but we have to show that there are free semigroup, and we may have to take powers of these elements, but we should not worry about that. So this is the most classical method to do that. In fact, in the paper of Eskin, Moses, and O, this is this method that they use. And the difficulty is produce sets like this. So you have to be smart to do that, I mean, in a very abstract situation. In this geometric situation, you kind of see how the sets are constructed. But this takes care of the case when you find a big element in this sense, which are not too far from the origin. But now I want to explain how to take care of the other case, which is the purpose of this lecture, actually. So this takes care, this is classical, and takes care of the first case. This is really something you'll find in many, many papers. Now, okay, so let me talk about the second case. All elements in this ball of radius 4 are small, that the displacement is less than a number. I can do even worse than that. Let me assume that all elements in the group gamma are elliptic. And this is a possibility, actually, that could happen. So elliptic elements with various fixed points. So we are in the case where the displacement is 0. But we have to show that the group, nevertheless, has uniform exponential growth. And this ping-pong technique is not clear to use, and actually I don't think one can use it. Okay, so the main idea now is, as usual, to construct a map So in the same spirit than what I've explained in the last two lectures, so I was constructing map from one negatively curved space to another, or from one space to itself, equivariant with respect to a group action. Here, we'll construct a map from the Cayley graph of the group with this distance onto the space X. So the map is just sending the Cayley graph. So let me put some relations. Okay, this is a graph. That's sufficient. Onto the space X. So it's a way to put the Cayley graph in the best possible way into the space. So in fact, it's not a map, it's a family of map, F sub C. And the construction is done as always, but I will have to need to read my paper because I never remember the formula. Construction of this family of map F sub C. So it's again using a Poincaré series. So let's look at the following map from X to R, which to each Y, so maybe I need more room. To each Y, you can associate, so the sum over all gamma of something which resembles a lot to what I said yesterday. There was some exponential of difference of two Boozman. Here, Boozman is not necessarily well defined, so I'll use distances instead. So the formula is as follows: minus C distance of S to gamma. I'll explain in a minute. Exponential of distance in the negatively curved space of Y to gamma x0. So I look at some orbit. So the x0 is a preferred point where this L was achieved. Look at the orbit of this point as usual. Here is gamma x0. And you pick a point Y. And you look at distance from Y to gamma x0. This is exponential. You make the sum of a gamma coupled with this expression. I call it Y, but it's S. I'm sorry. What is Y? No, it's Y. I'm sorry, it's Y. So what is this S? Now this graph, which you can think of as a combinatorial graph, you can also think of a one-dimensional object. So the edges are interval of length 1. So S is a point on the graph, which may not be only at a vertex, but in the middle of an edge. So of course, there are some technical issues which are not too difficult to take care of. For example, this ds is not really regular because there are closed paths. But I mean, let's forget about this. It's not too difficult to take care of that. And I mean, I let you check, as I did twice, that this map is strictly convex. So strictly because we have this exponential here, and goes to infinity with Y. And it's defined for C big enough. One issue today, well, I won't give all details, but is to estimate the best C, best possible C, which is some version of the critical exponent. So the best possible C is some version in this setup of the critical exponent. Not exactly, but I mean, you can think of C as being this. All right. so that it defines, so this defines a map just by saying that f sub c of s, this s here, for c big enough, is the unique critical point of this function. As you see, I'm repeating every day the same thing. And if you would ask me to give a talk tomorrow, I would do the same. But not Friday. Okay, so as yesterday and the day before, let me just state a couple of properties of these maps. So first of all, FC is equivariant. That is, the group gamma acts on its Cayley graph, just for translation. It acts here. So we can talk about equivariance. Maybe I should keep sigma for the generating set. This is true by construction. More interesting is that FC is Lipschitzian, Lipschitz, with constant less than C. That is FC of S minus, distance between, in X between FC of S and FC of S prime is less than C times S minus S prime. Which is a very strong property, and this is the version in this context of this volume contracting property. Here it's Lipschitzian. Okay, and a few other properties which I do not need. All right, so this is the construction, and now we can do the proof. Well, so let me give a heuristic proof, a wrong proof. I must admit it is a very strange proof. So let me give a heuristic, but say wrong proof. It's not true that it is wrong. I should erase this. It's not complete, say. Heuristic proof. If we would be alone, I would have written wrong, but there is the camera, so I must prefer not to do that. I'll make an assumption to make things easier. So let us assume that there is some asymptotic stretch. So what is it? If you look at distance between x0 and gamma x0, so it is the way the element gamma acts on x0 and its distance, and you may compare this to the distance in the Cayley graph from the identity to gamma, which is nothing than the length of gamma. So we are comparing, we are computing the stretch of gamma in the sense that gamma has a certain length and it displaces in the manifold of a certain distance. And we compare these two. And I make the assumption that this has a limit which is constant when gamma goes to infinity, whatever that means. That means when you take very long words. Take very long words and you look at this limit. It never exists, or almost never. But let me assume that you get a number at the limit which is some kind of asymptotic stretch. So that was the wrong part. I mean, this almost never exists. Well, it exists in certain circumstances, but not in full generality. But let's assume that is asymptotically, every element of the group, they stretch the distances from a certain factor, which is this number E. Okay, so it means, and here I'll be lousy, that the distance between x0 and gamma x0 is yeah, is something like E times the length of gamma, which I write like this, distance on S from E to gamma. So it's just a multiple of the length of gamma, as if the action was homothetic. Now let's come back to the Poincaré series, which I was stupid enough to erase, which is the sum of a gamma of E to the minus C distance. Well, let me take S gamma, and let me take x0. I want just to compute. So I want just to compute the rate of convergence, and the critical exponent, it does not depend on the point you start with. Let me start by the entity. So it is indeed the Poincaré series of the situation. And let me do something which is not correct. This is the wrong part of the proof. I just plug this inside. Okay? So this is supposed to be close or even equal, since I'm doing wrong thing, to E to the minus. So what we get? C minus E, distance on the group, A to gamma. So now I have a sum of exponential of distances on the group, on the Cayley graph, if you wish, this exponential of distances. So it's like an integral of an exponential of a distance. If we integrate by in polar coordinates, we know that the best possible number is exactly the growth rate of volume of balls, just by integrating in polar numbers. So the best possible number is something like the entropy of gamma with respect to S. So that the best C is like E plus this number we are looking for. So, of course, I'm cheating a lot here, but it doesn't matter. Anyway, the time is running fast. I'm almost finished. So now I need to draw two pictures. So the point x0 was chosen so that the generating element, let me assume that there are two, would displace this point of a distance which is exactly this sigma 2, sigma 1 of x0, exactly L. And this number here is some kind of asymptotic stretch. So I'll draw a picture of what happened in negative curvature. So let me, for example, iterate this one, sigma 1. So it's displaced sigma 1 of x0, then sigma 1 squared x0, and so on and so forth. So in negative curvature, the picture is like this. So this is, say, sigma 1 to the n at x0. Now, if you look at the distance here, which is the one which appears here, for gamma equals sigma 1 to the n, then it is usually much smaller than n times distance x0, sigma 1, x0. So this is on the picture of negative curvature. Of course, I'm being lousy, but I will finish by giving a precise estimate. But now if you divide by n, and you let n go to infinity, you get this number E. So what I'm saying is that this number E is much smaller than L. So because of negative curvature, and I'll give a precise estimate in a minute, the asymptotic stretch is much smaller than the local stretch, unless all these points are on the same line. And that would mean that the whole group would preserve a line, and if the group preserves a line, then it is almost a billion. And we have made the assumption that it was not. So the assumption that we made at the beginning means that we are more or less in this kind of geometric situation, which can be, again, I'm saying that it can be made very precise, and so that we get this inequality here. So that here, the best possible C is, so how did I write it? Entropy S of gamma plus L plus E minus L. Let me write it this way. Okay, now I can finish the proof. So maybe I'll put this here, keep this on the blackboard. I can finish the proof just by looking at the image of one point. So let me look at the image of the identity element by this FC. Well, this is a point which is not necessarily x0. So it's some point x. And I do the final computation here. And let's look at the distance between F, C of E and some element of the generating set, which I call sigma of FC of E. So because this is not x0, and by definition of L, this implies that there is an element sigma in S, so that the displacement of sigma at this point x is greater or equal to L. Well, this, yes?
Is FC an implicit function?
Yes. So we don't know where it goes. So this is the definition of L. This L was the max over all generating element of the generating set, and the infimum. And the infimum was achieved at x0. We may not be at x0, so we have not reached the infimum. So there is at least one element in the generating set where this is achieved. And I take this one. So now I write down this equivariance, C of E, F C of sigma. Okay? So this is x, sigma x. By this is greater than L, greater or equal to L. And here, I've used equivariance in this equality. Now I can use the fact that this map is Lipschitz, so that this is less than the distance in the Cayley graph between the 2 points E and sigma. Okay? But this is an element of the generating set, so this distance is 1, so this quantity is C. And what we get is that this number C, which is, because of all this abuse that I made, entropy of gamma plus E, satisfy this inequality, entropy of gamma plus E, plus L, I'm sorry, plus L is, no, plus E, that's correct. Is greater or equal to L, which implies that this entropy of gamma with respect to the generating set is greater or equal to L minus E. And this is strictly positive by my remark. So this is the lower bound we can produce. Of course, we have now to estimate this precisely. And I'll draw a picture and tell you how one can estimate. But this is the way this map can produce such an estimate. I mean, in fact, C is given by this expression. So it's more or less a lower bound on C. On the other end, we have another lower bound. And in spirit, we compare the local displacement with the asymptotic displacement. And the gap between the two, if any, if there is a gap, gives a lower bound for this entropy. So the question is there a gap? Well, if there is no gap, the group preserves a line, and it is almost abelian. So let me give one precise statement, which is a geometric idea. Just mention how the geometry comes in the story, and that will be finished for that. So I have assumed that my element, so let me take sigma, and I have assumed that the element was elliptic. So it has a fixed point. Say y here is a fixed point, okay? And we are working at the element x0. Certainly x0 is quite far from the fixed point because the displacement here, as we saw, is L, which is not 0. Now look at iterate of sigma. Then the picture is like this. Okay? And what I want to measure is the defect between this and the sum of these two distances. This is L again. So the formula that you can check now by comparison is that the distance between x0 and sigma square of x0 is less than twice L minus eta, where eta is the following number. So let me 12 minus, no, it's twice, I'm sorry. I've written two different ways of estimating it. It's twice the distance between x0 sigma x0, which is the same as this one. And there is a defect, which is 1 minus some universal constant divided by hyperbolic cosine of L over 2, where L is the quantity that we had. And I recall that L is greater than the Margulis constant, so we could just put here the Margulis constant. Okay, so the picture that I draw over there can be made very precise by estimation and triangle comparison. Again, we come back to this triangle comparison story. And the rest of the proof can be made correct. It's not here. All right, so that closes this. So I had prepared much more than that. And it's almost 3. So let me, I have tried to show you a different kind of problems to which you could apply these techniques. So from Mostow theorem, groups acting on manifold, and this kind of things which are more exotic. So in this spirit, the previous work was very old. The second has been published recently, and this is just submitted. I hope it's correct. And now we're working on something else, which is closely related to number theory. So let me just mention the problem. And if we can solve this conjecture, maybe next time I come here, I hope to be able to explain the proof. There is some kind of race in my department. I'm trying to solve with my colleagues, we are trying to solve this conjecture before Hervé solved the Canon's conjecture. But to be honest, I think he won't do it. We'll do it before him. Okay, so this is there are close relation between groups and number theory. So let me mention one problem which I like very much, which is the so-called Lemmer conjecture. And I'll take just 5 minutes. So this concerns roots of polynomials. So this is a polynomial with integer coefficient, which we assume to be irreducible. And monic, that is, it starts with 1. How does it work? A1 or an minus 1, which is much better. Okay, and you look at the roots of this polynomial, which are algebraic integers. And the question is the following. So you look at this number, I don't want to say wrong thing, which is called the Mahler norm. Of the polynomial P, which is the product of
these quantities, that is, you make the product of those roots of the polynomial whose module, because they could be complex, is greater than 1. So you get a number which is strictly greater than 1. And the conjecture that Lemmer stated in, I think it's 1933, is that if this is not equal to 1, then it should be bounded away from 1. And there should exist a number C which bounds this away from 1, where C is universal. Well, 2 comments. It's not difficult to see that if m of pi is equal to 1, all roots of module 1. You can forget about this. So if there is at least one root whose module is not equal to 1, then this m of pi is strictly greater than 1. But, I mean, it depends on the degree of the polynomial. And it could become closer and closer to 1 when the degree goes to infinity. The Lemmer conjecture is that this is not the case. It's bounded away from 1 independently of the degree. In fact, Lemmer used that to produce, so his goal was to produce large prime numbers. What does this has to do? Well, I don't resist to the pleasure to give you the best known polynomial at the moment, the one which corresponds to the lowest known value. Well, I say at the moment, it was last week, so maybe it has changed. So if you take this polynomial here, so x to the 10 plus x to the 9 minus x to the 7 minus x. 5, 4, 3 plus x plus 1. Then you can check that its Malheur norm is something like 1.762, 80, 81, etc. So this is a polynomial which is known at the moment, which has the smallest Malheur norm. And in fact, there is a strengthening of the conjecture which amounts to saying that this is will be the minimal value. So this number C could be taken to be the Malheur norm of this polynomial, that is this number over there. So we are very far from that. I will finish just by explaining how this is related to what I've explained. Well, it turns out that from any polynomial, you can produce a discrete group, a group acting on a product of, well, assume that the roots are real, to make it simpler. So on a product of copies of H2 of the hyperbolic space, a number of copies being the degree of the polynomial P. So you can produce from the polynomial, and it's not very difficult, a group which acts on this space by isometries, of course, and which is discrete. The action is discrete. So that there is a quotient, which is a manifold, or at least an orbifold. And it turns out that Breuer proved, well, he proved, or it was known before, it seems to be quite easy, that the logarithm of this Malheur norm is bounded below by the entropy of this group, I call G, with respect to a fixed generating set. So answering the question would be a consequence, positive answer of finding a number which bounds these entropies. So you have plenty of groups, as many as polynomials, and you want a bound which is universal. Okay. But here, the story about free group does not work. One can show that the
the free groups that you can produce in these groups are very far away from the identity when you go up in degree. So you lose the property, you cannot use this property of having subgroups which are free to produce that. And we hope that our method will allow to get around this free groups lack. So I had more description of this group G and the action, but it's maybe too late to do that. Okay, so before I finish, I'm happy also to thank the IMPA for the invitation and the staff for the movie. I hope to see me on the internet, right? Yeah. Okay, thank you very much.